So good evening, High Legh. Pleasure to be back again and talk to you. As we've said, this is going to be a short talk because it's just supposed to be a taster to throw out a few ideas that hopefully will then spur on a few questions in the more extended Q&A later. That's the idea anyway. So this is a 2-year update because Christmas 2021 seems like a long time ago now, but 2 years ago the James Webb was launched. And it was packaged up onto a rocket and sent out to L2, where it's currently parked 1 million miles above midnight. And I'm not going to say how they deployed it, how they got it there, why it's at L2, because that's all going to be covered in next month's talk. What I'm talking about is what James Webb has been doing as a sort of an update. So a year or so ago, I gave a Christmas update, JWST+2, and I figured that, well, probably about due for another update. So I'd give an update as to where we're at in terms of what has it been doing in 2023, because we got a lot of media attention in 2022 when it was first operational, but what's it been doing in 2023? So a reminder of one of the purposes of the James Webb. One of its jobs, if you like, is to look back in time as far as possible. So we know on this timeline of the universe, there's the Big Bang on the left. You can tell it's a Big Bang because it says kaboom in the top left-hand corner. And we are over there on the right, 13.8 billion years later. And the question is, if you can see greater and greater distances, then you can see further and further back in time, but just how far back can you go? Because one of the big mysteries at the moment is just when did the first stars and when did the first galaxies form? We know it wasn't in the last few billion years because Hubble has already looked back for more than 10, 12 billion years, and we still see galaxies. We don't see the earliest stars. We don't see the earliest galaxies. So we think all the interesting stuff in terms of the first stars and the first galaxy formation occurred in something like 500 million years, certainly within the first billion and possibly the first 500 million years. So if that's when the first galaxies and stars started to form, that's where we would like to probe. Hubble has gone back about as far as it can go, and hopefully the James Webb will go a little bit further. If we blow that first 500 million up a bit so that we're looking at the Big Bang and then a few 100 million years after that, well, at the moment, the Hubble has got back to about there. The Hubble, by looking at the most distant galaxies, the faintest galaxies that it can see in the visible part of the spectrum, we get back to about 500 million years after the Big Bang. James Webb works in the infrared, and a lot of these galaxies, because of the expansion of the universe, the light from these galaxies has been stretched out into the infrared, so hopefully they will be rather brighter in the infrared than they are in the visible. So with that, and the fact that the James Webb has got a much larger mirror than the Hubble, something like 6 meters rather than 2 and a bit meters, then hopefully it should be able to see much fainter galaxies, which are much more distant, and hence push back to the earlier parts of the universe. Quite how far will James Webb be able to get? Well, we don't know exactly, but we hope it'll get down here somewhere, to the first 100 or 200 million years after the Big Bang. It's not there yet. Only just started its life, its scientific life of taking data, but that's the aim, to get back and see where those first stars and first galaxies are being born. That's one of its jobs. Its other job, in a sense, because it's working in the infrared, is to see inside those very dusty environments that optical telescopes find so difficult. So, for instance, very early star birth within our own galaxy. What's going on inside nebula where the first stars are being born, some new stars are being born, and those planetary systems that are being developed around those stars. Very dusty environments. Dust scatters optical light much more than it scatters infrared light. Therefore, infrared should be able to probe these and see much more detail. So it's looking back as far as possible in time and looking in very dusty environments. They're two of the major arms of the JWST research. So 6 months or so after it was launched, we got the first press release. So that was back in 2022. So I'm not going to talk about that because that's what I talked about over a year ago. So let's have a look at what happened in 2023. So I'm not going to talk about all of the science that's come out of the James Webb, because there's far too much of it. If any of you actually keep an eye on the NASA web pages, you'll see NASA or ESA or the Canadian web pages. They all tell you what's going on almost day by day, and I've simply cherry-picked a few highlights, roughly speaking, one highlight every month for the last year. So back in January 2023, they released this, which perhaps doesn't look that spectacular, but what we're looking at is the dusty environment of a solar system seen edge on. So we're looking at a lot of dust that's probably being produced by a lot of planetesimals, a lot of dust and rocks that haven't yet formed planets or have tried to form planets and keep getting broken up. So we have a very dusty environment. The star itself has been removed, hence the 5-pointed star in the middle telling you where the star used to be before it was digitally removed in order to see the rather fainter dust around this particular solar system. For those of you who've ever been to nice dark sky sites, you may have seen the zodiacal light yourself, a band of light that you see either in the evening or in the morning that basically goes through the ecliptic and comes up quite a few degrees above the horizon. It's effectively the dust in the plane of our ecliptic reflecting light from the sun. So you tend to see it after sunset or before sunrise. So basically we're seeing zodiacal light from another solar system. Given how faint it is in our solar system, the fact that we can see it in a solar system that's, I can't remember exactly how far away, is pretty amazing. In February 2023, no, this is not a real image, this is an artist's impression of an asteroid, 150 meters in diameter, that James Webb discovered. Now that in itself is not particularly amazing. We're always finding asteroids and lumps of rock floating around. But 150 meters is not particularly large. It's still a problem if it were to hit the Earth, but it's not particularly large. And anything that small, we tend to see only when it's quite close to Earth. But James Webb picked up this 150-meter rock when it was still in the asteroid belt, 100 million kilometers away, not grazing the Earth, not passing by, but still in the asteroid belt. So that gives you an idea of the sensitivity of James Webb instruments. They actually caught it by accident. They were looking for something else entirely, and somebody noticed on a particular image there was a dot which they later realized was this 150-meter asteroid. So the good news is the James Webb has the sensitivity to see relatively small chunks of rock even when they are still way out there in the solar system before they become a threat. The bad news is James Webb isn't looking for these. This one just happened to be picked up by accident. James Webb hasn't got the time to go searching for little lumps of rock in case they come our way. That is left for other telescopes, such as the Chamonix telescope that's in the Vera Rubin Observatory that will be doing a survey and hopefully picking up a lot of these objects on a routine basis. This one just happened to be caught by accident. March 2023, James Webb released this image of a Wolf-Rayet star. It is thought that a lot of stars, before they go supernova, very massive stars coming to the end of their life, before they go supernova, might go through what is called a Wolf-Rayet phase. A lot of stars, Wolf-Rayet stars, appear to be very active and appear to be shrugging off an awful lot of material. And some people think maybe this is a precursor to a supernova. This particular star has almost certainly been shrugging off material for thousands, possibly even tens of thousands of years. This rather knotty structure that you can see in the nebula surrounding this star is effectively the outer atmosphere of this star that's been shrugged off over the millennia and basically producing its own nebula. This star is calculated to be something like originally maybe 40 stellar masses, very heavy compared to our sun, but it's already lost about 10 solar masses just from the amount of material that's shrugged off into that nebula. So the star itself at the very center there is perhaps 30 solar masses. Still a very good supernova candidate and one that's worth keeping an eye on. Whether or not Wolf-Rayet stars are indeed a precursor to supernova, well, we haven't watched them for long enough to tell yet. So we're going to keep an eye on lots of these stars. April 2023. The James Webb had a look at the planet Uranus. And this was seen in 1986 by Voyager 2, but bear in mind, although Voyager 2 got a much closer look, Voyager 2 went sailing past on its way to Neptune, so it was only close to the planet for a few hours. So although it had a chance of getting a very close-up view, when Voyager passed Uranus, it unfortunately didn't see anything of interest. It was almost a blank canvas. And it just so happens there were no interesting weather features, no storm features visible in the hours that Voyager 2 passed by. But now we have a look again from the James Webb. We see not only the surface detail, but we see the ring system very brightly because of the way it reflects infrared light. And in this case, we also see an interesting feature. It looks like the polar cap pointing towards the sun becomes unusually bright. Remember, it's got a very odd tilt, this particular planet, so it sometimes points at the sun, sometimes points away from the sun for the northern hemisphere. It looks like when it points towards the sun, the polar cap brightens considerably, and it also looks like there's perhaps a storm system visible just on the limb of the planet here. So bear in mind that although Voyager would have had a much closer view and in principle higher resolution, it only had that for a short length of time. James Webb can in principle revisit this as often as it likes, time of course being a bit of a premium on a premium telescope, but in principle it could revisit the planet once every few weeks for years into the future and watch these storm systems develop. So that's an advantage of having a James Webb-based view of the solar system from a great distance rather than a spacecraft view very close, but only for a short length of time. In May of 2023, this image of the star system, the planetary system around the star Fomalhaut, the brightest star in the constellation of the Southern Fish. And again, the star itself has been removed, hence the black circle right in the middle. So we're looking at the relatively faint, dusty environment of this particular star. And the James Webb has managed to see in unprecedented detail structure within what is assumed to be a planet-forming disk around the star. So it looks like there are a number of planets in this system that are all sweeping out and perturbing and hence producing this bright, dark pattern within the ring itself. In effect, what we're looking at, if you want to draw an analogy with the solar system, we're looking at the brighter outer ring is something similar to our Kuiper belt, and one of the brighter inner rings is somewhat similar to our asteroid belt. And there are other planets in there that are perhaps a little bit too faint to image as individual planets. But by looking at lots of planetary systems like this, we should get a very good idea of the formation of very early planetary systems. Again, it's very difficult to do this with any telescope other than the ones that are very sensitive to the infrared because they produce very bright images of these very dusty environments. In June 2023, they released this image of the Pandora cluster. This has been imaged before by Hubble Space Telescope, and the Hubble Space Telescope and the James Webb Space Telescope will have very similar sort of resolution in terms of the detail they can show. But if the objects are very distant and very red, then the James Webb, with the larger mirror and the greater sensitivity to the red end of the spectrum and the infrared, will pick up fainter objects. So although this has been imaged by the Hubble, the James Webb is able to pick up a lot of fainter detail. And this particular image is actually a mosaic of 4 images. It took quite a few hours to go this deep. But still, we're picking up a huge number of individual sources. Obviously, some in the cluster itself, some of the larger ones, but effectively, everywhere you look, there are a whole load of galaxies in the background. It's a little bit like the Hubble Deep Field, which took a very long exposure. Here, in only 4 or 5 or 6 hours, we've managed to get a huge number of distant galaxies. Somebody has calculated the total number of sources of light in this image is something like 50,000. So that will keep PhD students going for quite a while to actually start analyzing the colors and the shapes and the distributions of all these galaxies, as well as the principal cluster itself. Some of these more distant galaxies will be imaged because of the gravitational lensing effect of the cluster itself. In July 2023, it celebrated 1 year of science operations. It took about 6 months to get everything calibrated and working from a launch on Christmas Day to the middle of the next year. So this is 1 year of science operations, and they celebrated by taking an image of Rho Ophiuchi, which is one of the closest star-forming regions to the solar system. It's about 400 light years away. That's relatively close compared to most other star-forming regions, and it's obviously a beautiful image because it has so much interesting structure and interesting color. There are jets at the top there in red. These are hydrogen jets formed by very young stars being born, and there's a rather massive star at the bottom here that seems to be excavating a little cave inside this sort of yellow nebula at the bottom. I was quite intrigued by the fact that they chose Rho Ophiuchi because it's a popular target with amateurs because it's so colourful, but I couldn't figure out exactly how that related to the sort of picture that most amateurs would take. So if you'll excuse a very short diversion, I looked at the rather colourful Rho Ophiuchi taken with, again, this is an astrophoto taken with just a camera and a telephoto lens, and I thought, where in there is the James Webb image? It's obviously going to be fairly small, but I tried to tie it down. It took me a while to realise that if you take that section and blow it up, and then take that section and blow it up, then eventually that smudge there, which is about 1 pixel in my image, that's the James Webb image. You have to remember the focal length of the James Webb. The focal length of my lens there was 135 millimeters. The focal length of the James Webb is 135 meters. So it's 1,000 times the focal length. So not surprisingly, it's got a field of view which is rather tiny. But it was interesting just to be able to say, yeah, that pixel there is what the James Webb imaged for its first birthday. Okay, August, so we're more than halfway through the year now. So August 2023, it went back and imaged the supernova 1987A that went off in the Magellanic Clouds. And what they have been watching, Hubble has been watching for quite a few years, and James Webb will now continue watching for hopefully another 5 or 10 years at least into the future, is what's happening with this ring around the supernova. Just like the Wolf-Rayet star we saw earlier, it looks like the supernova, the star that eventually was the precursor for the supernova, that star has been shrugging off a lot of material for many centuries and probably many thousands of years. A lot of material has been lost from that very massive star. Then eventually it went supernova and produced an enormous, for the want of a better word, explosion. It's not a very good word to use for supernova, but it will do. So there's a lot of material in the interstellar region around this star, and then it goes supernova and produces shock waves, and the shock waves catch up with all the material it's been spitting out for the last 5,000, 10,000 years or so. And this little pearl necklace that you can see here in the middle of this nebula is the result of a shock wave hitting the material that was expelled thousands of years ago, because the material is expelled at relatively low velocities, and the shock wave comes out at not obviously close to the speed of light, but at a fair fraction of the speed of light. The shock wave is coming out and catching up with all the material released centuries or millennia earlier. And so it'll be interesting to watch this shock wave as it goes through the nebula created by the star losing mass in the past. And hopefully it will continue to do that and keep taking images every year or so that we get a movie of seeing this shock wave expand. In September 2023, we got an image of a very early birth of a star. This is really early on. You know that our sun will last for a few billion years. It's already been burning hydrogen into helium, nuclear fusion. For 5 billion years or so, it's got another 5 billion years ahead of it. Some small stars might last for 1 trillion years. This star is probably only a few thousand, maybe tens of thousands of years old. It is very, very early on in its life, barely initiated thermonuclear fusion. You can't see the star itself, excuse me, lasers don't work too well. The star is right there in the center, and even James Webb with the infrared finds it difficult to see what's going on right in the center there. But this protostar, this very early star, is forming and producing these jets that are coming out in 2 directions. Jets are quite common when stars are forming. They seem to be quite common in other phenomena, like black holes, for instance. But the mechanism by which infalling matter results in lots of material coming out in 2 specific directions, the mechanism that does that is still poorly understood. But these jets are coming out and again generating shock waves, because these jets are spitting out material at a fair fraction of the speed of light, which is coming out and then smashing into the interstellar medium, which is producing these shock waves. It's interesting to note that as well as getting an idea of the early star formation, people have been analyzing the very early parts of these jets, and they've looked at the jets on one side and the jets on the other side, and they think those jets are wiggling, and they can't simulate how those jets would wiggle unless there are two stars in the center. They think this is the birth of a binary star, and the binary star is actually producing these jets and producing the wiggles in these jets, which you might not be able to see because some of the detail is very small there. But it's interesting that we could be actually witnessing the birth of a binary star. Again, more of these systems need to be studied. In October 2023, getting towards the end of the year now, they saw one of the brightest gamma ray bursts that appeared in the sky, GRB for gamma ray burst. It looks pretty unspectacular here, this red dot, but it was visible in lots of different wavelengths as well as gamma rays. It was visible across most of the electromagnetic spectrum, and it was described as a kilonova. Just like a star that brightens a little bit is called a nova, if a star brightens a lot, it just generally gets called a kilonova to indicate that it's brightened something like 1,000 times more than you might expect for a nova to change brightness. And there's a couple of interesting things about this kilonova. They've determined it's most likely the result of the collision of two neutron stars. So it produced gamma rays, and it produced a lot of visible light. It obviously produced a little bit of infrared light as well. But the collision of these two neutron stars, they think occurred for these two neutron stars that were at that position, but they actually came from that galaxy. In other words, that galaxy actually, you notice it says on the label there, former home galaxy. They think what happened is when these two neutron stars formed, possibly an awful long time ago, I don't know, maybe 500,000 years ago, when the neutron stars formed in the first place as a result of possibly a supernova explosion, they got such a kick, they ended up getting shunted out of that galaxy, and for the last 500,000 years, they've just been drifting through space until they eventually merged with each other, just like black holes merge and give the gravitational waves that we see in the gravitational wave observatories. This happened with these two neutron stars and produced the gamma ray burst. So tracking it back to that host galaxy, I think that was the only galaxy they could find that could possibly have been the original home of those. But one of the biggest contributions of the James Webb, given that this was seen in other wavelengths, was the fact by looking at the spectrum, they could tell what elements were being made by that collision of two neutron stars. And one of the elements was tellurium. For those of you who don't know the periodic table, that's element number 52. That is a pretty heavy element. And this is the first time that it's been effectively conclusively proved that if you smash two neutron stars together, you get very heavy elements. Until recently, we thought that most of the heavy elements came from supernova explosions, whereas now we think quite a substantial number of heavy elements might actually come from the collision of neutron stars. Admittedly, neutron stars themselves come from supernova, so it all ties back to supernova, but it's the actual collision of the neutron stars themselves that actually generates some of the heavy elements and might be responsible for some of the heavy elements that are around on Earth today. Going forward, this is still October 2023, but I thought this was a definitely worth showing, even though we're still just on October. The James Webb imaged the Crab Nebula, much as the Hubble Space Telescope did. And it's very interesting to compare the James Webb with the Hubble. The Hubble image was, I think, about 20 years ago. So the difference between the James Webb and the Hubble is not only the fact that it's imaged in a different wavelength, but it was taken 20 years later. The question is, can you see the difference in size if I flick back and forwards between the James Webb and the Hubble? If you just concentrate on some little bit of the structure there, can you see that the entire thing has got, perhaps if you look at that little loop at the top there, there's a definite change in size. These two have been very carefully matched together. The stars are absolutely lined up. So any differences you see in the nebula are the result of either the fact that you're imaging at a different wavelength, or you're seeing the nebula a few percent bigger. And if you think about when this went off, it was seen by the Chinese in 1054. As seen from Earth, it went off in 1054. So 20 years is a reasonable fraction of its entire lifetime, if you take 0 as being the date it went off. And so you would expect it to be a few percent bigger. And that's precisely what you see when you look at the detail. There are quite definitely changes. And so by comparing the picture now with the picture from 20 years ago at a similar sort of resolution, you can start to see how the supernova remnant is changing with time. The James Webb is also looking in detail at the elements here, the iron and the nickel, to try and get a better handle on exactly how stars go supernova when they come to the end of their life. Perhaps you also notice this rather more milky substance in the background, which is not so obvious in the Hubble picture, but is definitely everywhere in the James Webb picture. What we're looking at is so-called synchrotron radiation. This is the radiation that results from charged particles bending in magnetic fields. And the magnetic field is produced by the pulsar, the neutron star, at the center of this particular nebula. And we can't pin it down exactly, but occasionally you see some wispy lines that are effectively tracing out the magnetic field produced by the pulsar, in much the same way that when you look at the corona of the sun during a total eclipse, you see parts of the corona seem to be mapping out the magnetic field of the sun itself. So it's very interesting for a number of reasons to compare the James Webb with the Hubble images there. And I'll finish from the end of 2023, another collaboration, if you like, between different telescopes. Here, an X-ray telescope has identified a black hole by looking at the X-ray emission. That's the only way of explaining why we get so much X-ray emission from a particular point. But the same point in space has been identified with a particular galaxy, which the James Webb could pin down. So the James Webb can't specify there's a black hole there, but the X-ray telescope can. And the James Webb, by looking at the host galaxy for this particular object, can take the redshift of that, and it finds that the redshift is an enormous, z equals 10. A redshift of 10 means the light from this object has been stretched tenfold in order to reach us because of the expanding universe. So we get an idea of the distance. This puts us back squarely into the middle of that first billion years of the Big Bang. So we're not close to zero yet. We're not close to 100 million years. But we can quite definitively say black holes definitely existed 500 million years after the Big Bang. And it's a relatively big one. It must be a huge one if we can see it in X-rays at this distance. So we can say that black holes definitely, really big black holes, came into existence no more than 500 million years after the Big Bang. And so the theorists now have a challenge. Can you explain how they got so big so fast? It might be that if we keep pushing back these boundaries and go to earlier and earlier times, it might be that we see a black hole even earlier than 500 million years after the Big Bang. But at the moment, that's effectively the record, and that's the one that's got people scratching their heads. How can we come up with a mechanism by which black holes presumably grow to be that big that quickly? So that's a good place to say that 2023 has produced some very interesting images from the James Webb in collaboration with other telescopes, whether they be spacecraft or ground-based. And that gives us an idea that we can expect some wonderful things to come in 2024. So given that this talk was originally written as an anniversary of its launch on Christmas Day 2021, I usually end by wishing people a Merry Christmas, but it doesn't really seem applicable anymore, but I still think the James Webb picture pulled by the reindeer is very apt. Thank you all very much.